Good morning, dear students. Please confirm if my voice is clear. You are able to see my screen.
Yes.
So, in the previous class, we started discussing hybrid pi equivalent circuit of bipolar junction transistor, okay, or high frequency pi model of a transistor, okay, also called as dielectric model, right? We have seen that primarily we consider capacitive effects and delay, okay. Capacitive effects, RC combination gives delay, okay, and we have discussed that because the transistor provides current gain, okay, we have a current source, a dependent source, right? So all this we have discussed in the previous classes. Okay. Then we have derived the expression for the common emitter short circuit current. Okay, in the previous class, we derived the expressions for common emitter. Okay, this is the common emitter short circuit current. Okay, then what have we done? We did not derive for common base, but we wrote similarly. Okay, we wrote similarly, and we derived or we okay we obtained the expression for common base configuration. Common emitter configuration we derived, common base we did not derive. Similarly, we have mentioned and written expression for cutoff frequency and gain. Okay, right. So these are the expressions for the gain and the cutoff frequency. This we have discussed in the previous class. Then what we did is, see here. If we consider, okay, if we consider f alpha, this is the expression for f alpha, okay, and the expression for f beta, expression for f beta, okay, this one, okay, both have 1 by 2 pi rb dash e common, okay, f alpha 1 by 2 pi rb dash e common, okay. So eliminating the common factor, we can actually obtain the relation between f alpha and f beta. Simple math, okay. This is the relation between f alpha and f beta. Okay. Then, so what do we mean by f alpha? Okay, cutoff frequency. Now we have discussed that. Okay, in the previous class, previous classes we discussed that gain is whatever the maximum gain we have. Okay, and that divided by root. The value of 1 by root 2 is 0.707. Okay, the value of 1 by root 2 is 0.707. Whatever the maximum gain we have divided by root. So maximum gain here is HFE. HFE by root 2 is nothing but 0.707 HF. Okay. Now at that point, if we draw a line parallel to x-axis, this dotted line, where it intersects, that is the cutoff rate. Okay, so it intersects here. So this is the beta cutoff frequency. Fine. Then here, okay, I told 1 by root 2. Okay, whatever the maximum gain divided by root 2, right? That when we draw a line parallel to x-axis at that value, then where it intersects the curve, the corresponding x-axis is the cutoff frequency. Okay. So the same thing in decibel. Okay, the same thing in decibel. Decibel means 20 log of gain. Okay, decibel is 20 log of gain. The same thing in decibel is -3. Means whatever the gain in dB we have, -3 dB, there we need to draw a line parallel to x-axis where it intersects the curve, that is the cutoff. Okay. So normalized gain by root 2, maximum gain by root 2. Then for gain in dB, okay, maximum gain -3 dB. Okay, anyway, in simple words, what we have observed is, okay, this discussion also we completed in the previous class, that the gain of common emitter configuration is high, okay, but the higher cutoff frequency is low. Okay? Whereas for common base, see, this is common emitter, gain is high compared to common base. Common emitter gain is high. Okay? Why current gain is high in common emitter configuration? Because in, okay, in the common emitter configuration, okay, in the common emitter configuration, what we have is this common emitter. Emitter is common for both input and output. The input is base, okay, the output is collector. Usually base is very thin and lightly doped, because of which this current is very small, okay? And collector current is much larger. So current gain in common emitter configuration is high. Okay, and that is the reason. That is the reason we have high current gain. Okay, we have high current. Now observing the expressions of F alpha and F beta, what we actually understand is, see, this is F beta, beta cutoff frequency. So this one will be F beta. Okay? Alpha. So F alpha will be here. So by comparing the expressions of F alpha and F beta, right? See here, compared to F beta, okay, compared to F beta, right? So we have additionally this term. Okay? Then because of that, what we have is the value of F alpha is much greater than F beta. Okay. So based on this understanding, we are drawing F beta here. Okay. Then F alpha we are drawing here. This is it. Okay. Alpha cutoff frequency. Right. Then this one is the beta cutoff frequency. Okay. So far so far what we have done, we have discussed, okay, current gain in common emitter, we derived, okay, and we derived the expression for cutoff frequency also. Common base we did derive, similarly we have mentioned and we have noted now, okay, and based on the understanding of the values, we have seen that the gain in common emitter configuration, the current gain, okay, the short circuit current gain in common emitter configuration is high. Here cutoff frequency is low compared to common base. Common base has low gain. Okay. And higher, okay, cutoff frequency. Fine. So this we have, okay, completed. So next topic is gain bandwidth. Okay. Next topic is gain bandwidth. Okay. Now let us see the expression of current gain in common emitter configuration. Okay, this we derived here, right? What is the expression we have in common emitter configuration? So this one, okay, AI is minus HFP by 1 plus C into F by F. This we derived in the previous class. Okay. Then if you take the magnitude of that, okay, minus HFP by 1 plus J into F by F beta. So minus HFP magnitude if you take, it is HFP, okay, and any complex in the form of A plus JB, how will you take magnitude? Square root of A square plus B square, okay, square root of real part square plus imaginary part square, okay. Once again, let us see the expression for AI. This is the expression for AI, for common base configuration. So, sorry, common emitter configuration. What do we have? Minus HFE by, so if you take magnitude, minus HFE becomes magnitude is HF, okay, and the magnitude of this becomes square root of 1 plus F by F beta whole square, okay. So HFE by square root of 1 plus F by F beta whole square. So HFE by square root of 1 plus F by F beta whole square. Okay. So what we are taking is the AI magnitude we are taking. Okay. Then here we are defining one frequency FT. Okay, we are defining one frequency, which is simply in between the F alpha and F beta. Okay. So what we are considering now is, see, where this is beta, so this one is F beta. Okay. Here we have alpha. So this one is F alpha. We are considering a frequency in between this one and this one. Let us call it as F. Okay, so this frequency is actually F between F beta and F. So Ft is greater than F beta, and this Ft, okay, is less than F alpha, right? So greater than F beta and less than F alpha. Greater than F beta, less than F alpha. Okay. Now, how can we write this relation? Ft much greater than F beta. I can divide by F beta. Okay. So we have Ft by F beta, right? If we square this, okay. If we square this, then right. If we square and then divide by F beta. See this relation. Can write Ft by F beta much greater than 1, then square on both sides. Okay. Anything is already greater than 1. If you square also, it is, suppose 2 is, say, okay, 100 is much greater than 100 square, 10,000. Okay. 10,000 is also much greater than. So, what we are considering here is, we are considering this from the graph, okay, this one. Just a frequency between F alpha and F beta, we are calling it as F beta. Okay. And from that, dividing by F beta, squaring, we are writing this relation. Okay. Then what we will be doing next is, okay, Here, if we look at the expression, okay, if we look at the expression ft by f theta, okay, ft by f theta, and then hf. Let us see the graph. Here, okay, here, if we see, right, now at the frequency, see, this is our f, okay, this is our f. If you see this graph, what is happening to common emitter current gain at ft? This is ft, I told. At ft, the gain is becoming 1. Means when f is equals to ft, okay, right? In simple words, see, f beta is common emitter, okay? F beta is common emitter cutoff frequency. F alpha is common base cutoff frequency. This frequency ft, okay, the taking where the gain of common emitter configuration becomes 1. Means when f is equals to ft, in the expression of current gain in common emitter configuration, when we put f is equals to ft, okay, then the gain of common emitter configuration becomes 1. So what we are doing is, when f is equals to ft, gain is 1, okay. So actually this is 1 is equal to 1 is equal to hfe by square root of 1 plus ft by f beta whole square, okay. But just now we discussed that ft by f beta whole square is much greater than 1. So if you put ft here, then it is much greater than 1. That 1 we can write. So what we can write is, we can write 1 is equals to, neglecting this one, here we are taking 1, because when f is equals to ft, okay, this gain is becoming 1 from the graph. So 1 is equal to hfe by square root of, and we discussed when f is ft, this one we can neglect, okay. So 1 is equal to hfe by 1 if we neglect, square root of f by f beta square. Square root square will cancel, ft by f beta will cancel, right? So what we actually, okay, if we cross multiply this is the relation. Now if we cross multiply, ft by f beta is equal to hft. Then the f beta, if we cross multiply, this is the relation we get. ft is equals to hft by f beta. Okay. Now actually ft we define where ft is defined as the frequency at which the short circuit common emitter current gain has a magnitude of unit. Okay. So here the gain becomes 1, where the gain E gain, where it becomes 1, that we are calling ft. This is ft. Okay. Right. Now because of that, what is happening? And if we simplify the expression of ft we are getting hfe multiplied by fp. Let us see the graph and let us see what is hfe. Hfe is the gain, isn't it? Hfe is the gain. F beta is the cutoff. So ft we are getting as the product of gain and cutoff. Okay. F ft we are getting as the product of gain and cutoff frequency. Okay. Gain at low frequencies. Okay. F is gain at low frequency. Relatively lower. Okay. These are at higher frequencies. Relatively lower. So see, x-axis is frequency. So relatively lower frequencies, the gain is HF. Okay. So FT we are getting as the product of, okay, gain at low frequencies multiplied by cutoff frequency. Now usually bandwidth is higher cutoff frequency minus lower cutoff frequency. Okay. If you look at the typical values, I will show you the typical values of F beta. Okay. So usually lower cutoff frequency will be very small. Okay. Usually lower cutoff frequency will be very small compared to higher cutoff frequency. Okay. So we can approximate the bandwidth as the upper cutoff frequency. Okay. So you can say this is the bandwidth. Beta cutoff frequency or CE bandwidth. F beta we can call it as bandwidth. So FT is nothing but this is gain bandwidth. So product of gain and bandwidth is nothing but the F. Okay. So that is why the heading we have gain bandwidth product. Okay. FT we are starting. Okay. As the frequency at which common emitter current gain becomes 1, and when we derive we are actually obtaining that this is nothing but the gain bandwidth product. Okay. Now here see Epita is usually in megahertz. Okay, right, and lower cutoff frequency is somewhere in hertz. Right? So this megahertz minus few hertz, we can approximate it to be the nearly this much. You can see bandwidth is higher cutoff frequency minus lower cutoff. Higher cutoff frequency is in megahertz. Lower cutoff frequency is usually in few hertz. Okay, megahertz minus few hertz will be nearly megahertz. Okay, that is why F beta we can take it as the bandwidth. Okay. Then the expression ft we got this one just now we obtained previous f beta 1 by 2 pi r b dash e into b dash e plus c b dash c. Okay, this is the expression for it. Other than HFE, this we derived in the previous case. Fine. Then also, okay, in the previous class we discussed that, okay, GM is HFE is nothing but GM RB dash. This also we discussed in the previous class. How did we obtain this relation? Okay, how did we obtain this relation? By comparing, okay, by comparing this one with the H parameter. GM VB dash E, right? We can take approximately equal to HFE IP. Okay, GM VB dash E is HFE IP. This discussion we already completed. So for H parameter model, we have HFE IP here. For high frequency model, we have GM VB dash E. Right? This discussion we already completed, so please recollect. So GM VB dash E is equal to HFE into I. So HFE will be GM VB dash E by IB. VB dash E by IB we can take it as RB dash. So HFE we can take it as GM RB dash. Okay. HFE as GM, right? HFE we can take it as GM RB dash. This discussion already completed in the previous class. Okay. So So either we can represent this in terms of HFE or we can represent this in terms of GM. Okay, that is what we want to take. Now, see, usually the CB dash E is much greater than CB dash C. Okay, what is the reason for that is, see here, let us look at the transistor. Okay, let us look at the transistor. This is base emitter capacitance, then base collector capacitance. Base emitter capacitance. For a transistor to work as an amplifier, base emitter junction is what biased? Please tell. Base emitter junction is what biased? Yes. Emitter base junction is forward biased. Collector base junction is what biased? For a transistor to work as an amplifier. Please answer. You might have studied this in EDC also. For a transistor to work as an amplifier, emitter base junction is forward biased and collector base junction is, please answer. Fast please. Reverse biased. Okay. So this junction is forward biased. For a transistor to work as an amplifier, this junction is forward biased and this junction is reverse biased. Okay. Now, see, when we reverse bias, what happens? The charge carriers, okay, they move away from the junction under reverse bias. Under forward bias, the charge carriers move towards the junction. Okay. So, which case, see, now what we can do is, this junction I told you we can consider as a capacitor. Under forward bias, the charge carriers move closer to each other. Under reverse bias, the charge carriers move away from each other. Okay. So in which case, now we can, I told you we can consider this as capacitor. Which case, right? The plates of the capacitor will be closer, forward biased or reverse biased. Please answer. I told you this junction is for a transistor to work as an amplifier. The base emitter junction is forward biased. Base collector junction is reverse biased. Okay. Now, when junction is forward biased, the charge carriers move towards the junction and they recombine at the junction. Okay. So when they move, the equivalent is a capacitor with the distance between the plates, high or low. Please answer. Very easy question. Okay, right? See, it is like this. Under forward bias, the charge carriers move right towards each other. The net effect is a capacitor with the distance between plates. Okay, right? The distance between plates very small. Under reverse bias, what happens? You know, under reverse bias, the charge carriers move away from the junction, and at the junction, depletion region is formed. Okay. Now the depletion region gives capacitive effect, and this depletion region, okay, this depletion region, right? Usually under reverse bias, the depletion region will increases. So it gives capacitive effect where the distance between the plates is large. Okay. So what I am trying to say is the equivalent here we can consider a capacitor with larger distance between the two plates. Here you can consider capacitive effect with smaller distance between the two plates. C epsilon A by D. isn't it? Capacitance. The expression for capacitance is epsilon A by D, where D is distance between the plates, isn't it? So capacitance is inversely proportional to the distance between the plates, right? We discussed that for this forward biased junction, okay, the plates are closer. Under reverse biased junction, the plates are separated, the capacitive plates. Okay. So now tell me which capacitor value will be high. Which capacitor value? See here, distance is less. Distance is less means epsilon A by D. C is inversely proportional to distance. Distance is less means capacitance is high. Distance is more means capacitance is low. So usually the base to emitter capacitance is much greater than base to collector capacitance. Okay. So base to emitter capacitance is much greater than base to collector capacitance. Then what we can do is we can neglect this term. Okay. We can neglect this term and we can write Ft is nearly equal to Gm by Cb dash, or rearranging Cb dash C, we can write it as cross multiply Cb dash C side Gm by 2 by Ft. Okay. Then, right, Ft. Okay. What is Ft? HFE into Ft. We already discussed. So, what will F beta be from this? F beta will be Ft by HF. Okay. F beta will be Ft by HFE. F beta is Ft by HFE. So in place of F beta, this is the same old expression we derived in the previous case. In place of F beta, we are writing this Ft by HF. Ft by HF. Okay. In place of F beta, we are writing. Now, okay. Next, we here, okay. AI, okay. AI further, okay. You can write like this, just rearrange this numerator as it is. HFA we are pulling out, okay. 1 plus J HFE F by F. So actually AI is depending on HFE and FE, okay. Right. This is the conclusion. So with this we finish first unit, okay. One very small topic, please take it as homework, okay. It is derivation of, okay, derivation of cutoff frequencies for multi-stage amplifier. Okay, very easy topic, right? You do Google search, you will get. So take this as homework. Derivation of cutoff frequencies for multi-stage amplifier. Means if we consider multi-stage amplifiers, right? N number of stages. What is the overall cutoff frequency? Okay, what is the overall cutoff frequency? Right? Considering N stages. So take this as homework. Okay. And so we have finished first unit. Very easy second unit. Okay. See, first unit has so many derivations and all, right? And see, other than today's class, all the videos I have already uploaded. Okay, fine. Try to download all the videos. Okay, try to download all the videos. Right. Once you download, any number of times you can listen. Fine. See, just by reading, sometimes it may be confusing. But you see the video, then okay, has to be, you should be able to understand very easily. So I have uploaded all the videos. To this video also I will upload shortly. Okay, the same thing I have already shared in our group. Okay, the same thing I have already shared in our group. See this one. Okay, this one I have shared right on Friday. Okay, I have shared this on Friday in our group. Okay, 2:16 p.m. Friday 2:16 p.m. I have shared this. Now if you click on this link, okay, click on this link, then all our class videos will open. Okay, all our previous class videos will open. This is first video. If you go down, you can see all the videos. Okay, you can see all the videos. So try to download, try to download the videos. Okay, right, and watch it. See any number of times you can watch. Okay, until you learn it perfectly. Still, if you have doubt, don't hesitate to contact me. Okay, all of you have my contact number. Download these videos. Okay, first video, then here all the playlist. Download all the videos. Go through, and if you have any doubts, don't hesitate to contact me. Okay, we will have discussion over phone. Then I can open the video. Suppose you have doubt in this video. Suppose. Then you will tell. This analysis of CECC cascode using approximate H parameter normal, this state, I have doubt at so and so time. Okay. Suppose we have doubt somewhere here. Okay. 23 minutes 51 seconds we have doubt. Then what I will do, I will open that, I will watch, and then I will call you back and I will clarify. Okay. So in this manner, all of you should learn everything perfectly. That is the main idea. And any doubts? No doubts. We will stop the class here. Right? We'll complete the homework. Right? We'll continue the next class. Thank you very much.